In the last lecture, we have discussed base of a filter. Today, we will discuss some results related to base of a filter. We first discuss the difference between subbase and base of a filter. Let me recall you the results which we have proved earlier. Suppose X is a non-empty set and suppose A is a non-empty collection of subsets of X. Then we know that if A has the finite intersection property, then there exists a filter base B containing A. And how can we obtain filter base B from A? Let us recall that B can be obtained by taking finite intersections of members of A. And if we have a filter base B on X, then we know that there exists a filter F which contains all those subsets of X which contain a member of B. And so, if we recall the definition of base of a filter, we know that a subcollection B of F is a base of F if each member of F contains a member of B. And so, filter base B is nothing but base of filter F. And if we have a filter base, then by taking supersets of members of B, we can obtain filter F. And now we are in a position to discuss the properties of a base of a filter. Now the first theorem states that on a non-empty set X, a filter F dash with base B dash is finer than a filter F with base B if and only if every member of B contains a member of B dash. So it gives a relation between two base of two filters. Let us prove this theorem. Let every member of B contain a member of B dash. Then we have to show that filter F dash is finer than filter F. So take some member F of filter F. And since B is a base of filter F, and we know that every member of F contains some member of base B. And so there exists some member B of base B such that B is contained in F. And we have assumed that every member of B contains a member of B dash. So for this member B of B, there exists a member B dash of base B dash such that B dash is contained in B. Since B dash is contained in B and B is contained in F, and so B dash is contained in F. As B dash is a base of filter F dash, superset of every member of B dash must be contained in F dash. And since B dash belongs to filter F dash and F is a superset of B dash, so F belongs to F dash. We have shown that if F belongs to filter F, then F belongs to filter F dash. That is, each member of F is contained in F dash. Hence, F is contained in F dash. That is, F dash is finer than filter F. Conversely, let F dash be finer than F. Then we have to show that every member of B contains a member of B dash. So, take some member P of base B. As we know that if B is a base of filter F, so each member of B is contained in filter F. And so B belongs to F. And since filter F dash is finer than filter F, so B belongs to F dash. As B dash is a base of F dash and we know that every member of F dash contains a member of B dash. So for B belongs to F dash, there exists some member B dash of base B dash such that B dash is contained in B. B is any member of base B and we have shown that there exists some member B dash of B dash such that B dash is contained in B. Thus, every member of B contains a member of B dash. Now, the second theorem states that let X and Y be non-empty sets and F is a mapping from set X to set Y. Then the first statement is if B is a filter based on X, then the family C consists of F images of all members of B is a filter based on Y. The second statement is if C is a filter based on Y such that every member of C intersects F image of X, then the family D consists of F inverse image of every member of C is a filter based on X. Let us prove this theorem. Now we shall prove the first statement, that is here it is given that B is a filter based on X. If B is a filter based on X, then we know that a filter base is a non-empty family of subsets of X. So B is non-empty. This collection is non-empty and so C is also non-empty. As B belongs to, for each B belongs to B, B is non-empty because we know that no member of filter base is empty. So B is non-empty and so F image of B is also non-empty, whereby no member of C is empty. Now we have to check the second property of a filter base. Let f of B1 belongs to C and f of B2 belongs to C, where B1 and B2 are members of B. As B is a filter base, for B1 belongs to B and B2 belongs to B, there exists some member B3 of B such that B3 is contained in B1 intersection B2. Then F image of B3 is contained in F image of B1 intersection B2. But as we know that F image of B1 intersection B2 is contained in F image of B1 intersection F image of B2, so F image of B3 is contained in F image of B1 intersection F image of B2. So we have shown that for F image of B1 in C and for F image of B2 in C, there exists F image of B3 in C such that F image of B3 is contained in F image of B1 intersection F image of B2. We have shown the second condition of a filter is satisfied. We have shown that intersection of any two members of C contains a member of C. Hence, C is a filter based on Y. Next, we have to show that if C is a filter based on Y, then D is a filter based on X. As C is non-empty because C is a filter base, it is a non-empty collection of subsets of Y. So C is non-empty, then D is also non-empty because it contains inverse image of members of C. So D is also non-empty. And it is also given that for C belongs to C, C intersection F image of X is non-empty. We claim that inverse image of C under F is non-empty for every C in C. If possible, let inverse image of C under F is empty. Then we have two cases, either C is empty or no member of C belongs to the range set F of X. That is, C intersection F image of X is empty. But both the cases are not true. So we arrive at a contradiction as Y doesn't belong to C and C intersection F image of X is non-empty. Hence, inverse image of C under F is non-empty for every C in C. So phi doesn't belong to D because D contains uh, inverse image of every member of C under F. And since F inverse of C is non-empty, so no member of D is empty. Now we have to check the second condition of a filter base. So let inverse image of C under F belongs to D and inverse image of D under F belongs to D. As C is the filter based on Y, for C belongs to C, D belongs to D, there exists a member E of C such that E is contained in C intersection D. But this implies that inverse image of E under F is contained in inverse image of C intersection D. And this implies that inverse image of E under F is contained in inverse image of C under F intersection inverse image of D under F. As E belongs to C, so inverse image of E under F belongs to D by definition of D. So we have shown that for inverse image of C under F in D and for inverse image of D under F in D, there exists a member inverse image of E under F of D such that inverse image of E under F is contained in inverse image of C under F intersection inverse image of D under F. That is, we have shown that intersection of any two members of D contains a member of D. So second condition of a filter base is also satisfied. Hence, D is a filter base on X. As we know that any filter base is a base of some filter, so this result is also true for any base of a filter. Thank you.